Hello, everybody. I'm Thompson. This is my Lab 4 report. This lab is all about observing the oscillatory motion of objects that can be impacted by external forces such as spring, gravity, and drag. And we are dealing with the net force of the gravity in our spring. We analyze this data through predicted models such as the glow script code in our tracker video. And this lab primarily deals with concepts of net force, velocity, position, spring force, energy conservation, and the modeling of these concepts, along with the idea of a system for surroundings where the ball object is our system and the spring in the air and gravity is surrounding. Going into the results, this is the tracker program results. This is a screenshot of the program itself, and these are the X position over time graphs and the Y position over time graphs. This is the code snippets. These red lines are important information blocks I'll go into later, but as the code, and then this is the graphs produced by the code. This is the change in energy over time for kinetic and potential, and this is the X position versus time between the model and the experiment, and this is just a screenshot of the produced model. For the background of the experiment, this lab was all about analyzing the circular oscillatory motion of objects, or ball attached to a spring as impacted by gravity and spring forces. And so the primary equations used to produce this model were gravity, Hooke's law, velocity and position update equations, and the unit vector equations, along with kinetic energy, potential energy, and then the energy conservation equation. The starter code was updated with physics formulas that integrated the above equation into usable code to provide a relatively accurate model predicting the behavior of the spring ball system from tracker. And then after finishing the starter code proper equations, we were able to successfully model this behavior. And so as you can see with these underlined blocks, this is the gravity being included in the code. This is the um, spring force equation. This is just the net force. This is update equations for velocity and position. And then this all deals with unit vectors. And then this is kinetic energy and this is potential energy. All right, experiment results. Using the provided tracker video data, a CSV file was made that modeled the experimental X and Y behaviors. The oscillatory behavior from the tracker model was then predicted using simple Gaussian code, and this was taken with a CSV file to produce this model right here, which compares the model and the experiment data. And so what this does, this allows us to produce an overall model to see how close our predicted behavior was to the actual experiment. And as you can see, it's pretty close, so our Gaussian code did its job correctly and good enough. And then this is also just more of those um, kind of instances where we use physics formulas to produce this code. As for what does it mean, for the first part, if the energy principle is satisfied, yes, it is, because as you can see, for all of these parts right here, the spring and the gravity share an inverse relationship. So where gravity goes up, spring goes down. Where spring goes up, gravity goes down. This all results in an average of 0 for the net energy. So there's no energy lost or added. And then for part 2, for the X position data and the Y position data, the estimated period seems to be about 1.8 seconds for both. And the reason why this is the same is because they're pretty much just reflected graphs with the same magnitude, although different signs. And this kind of makes sense because the circular movement of the object, although, I mean, it's a little oblong, so it's going to cause some deviations in the Y part, but it does prove that there is an average similarity between the X and the Y that allows them to have this relationship right here. That's proportional yet opposite. That was my lab. Thank you for watching. All right.